All right, so today we'll talk about sound. So we talked about waves last chapter, and we talked about general properties of waves. Sound waves are mechanical waves. You need a medium for these guys to travel, unlike electromagnetic waves that'll travel in vacuum. So sound waves need a medium to travel. And there are sound waves can be longitudinal waves or transverse waves. When sound waves travel in a fluid, fluids do not support shearing stresses. So in a fluid, sound waves are only longitudinal. So for instance, when somebody's talking, that wave is traveling through air, which is a fluid. So we have a special name for that fluid. It's a gas, but in fluids and gases, only longitudinal waves, sound waves travel. But a sound wave traveling through Earth can be both longitudinal and transverse, and we call those earthquake waves. All right, so we are studying about sound waves today. These are some of the topics we'll cover. It turns out that the speed of the wave depends on the property of the medium through which it's traveling. We'll look at 2 and more sound waves reaching a particular spot and how they combine. So we'll look at interference. We'll look at intensity and sound levels. Intensity is related to how much energy is passing per unit area per second. And the loudness level is how loud the sound we perceive it as. Okay, so we'll talk about all of that. The Doppler effect is, let's say a source produces a certain frequency of sound, and if you're moving or the source is moving relative to you, the perceived frequency would be different because of the relative motion of the two. And that's the Doppler effect. And we'll look at shock waves. These are something that are generated when the source moves faster than the speed of the wave. Okay. All right, so those are some of the topics we'll consider. So let me show you a speaker first, how sound waves are produced. Okay, let's see. There you go. All right, so here's a speaker. Here's a model of a speaker. This is a magnet. And what this is an electromagnet. You'll learn about this in physics too. Okay, so these arrows are currents. So when a current passes through this coil of wire, it becomes magnetic. When there's no current, it's not a magnet. So when the current passes, it becomes magnetic. And depending on the direction of the current, this can be a north pole or a south pole. Okay, so when the current is in one direction, this is attracted to the magnet, and when the current is in the other direction, it's repelled by the magnet. So by passing a current through this coil, you can make it move back and forth via the magnetic forces. And this coil is attached to a diaphragm, and the diaphragm moves back and forth. So to produce sound in this region, all you have to have is this diaphragm move back and forth. And so what a speaker does is it converts electrical signals into mechanical motion, which produces sound waves in this region. Okay, so that's how a speaker works. Yeah. So when a diaphragm moves back and forth, it's producing sound in this region. And interestingly, as speaker oscillates back and forth, so as this oscillates back and forth, it transfers energy to the air, mostly as thermal energy. And most of the energy transferred is just converted to heat. Only a small part, about 1% of the speaker's energy goes into compressing and expanding the air. So only 1% of that is converted into sound energy. Okay. And into sound waves. So when this speaker goes in back and forth, 1% of the energy goes into compressing the air, and this is lower pressure, higher pressure, lower pressure, and higher pressure. Compressions and rarefactions, as they're called. Okay. And this constitutes sound waves. So what this is saying is if it's a 100-watt speaker, about 1% of that gets converted to sound waves. 1 watt gets converted to sound waves. Okay. So sound waves, okay, so the compressions and rarefactions move out as longitudinal pressure waves, having the same frequency as the speaker. So the frequency of this sound wave is the same as the frequency of the speaker at which it's vibrating. Sound waves in fluids are longitudinals because fluids have no shear strength. In solids, sound waves can be both transverse and longitudinal waves. Okay. Okay, well, let me also show you another simulation. Okay, so here's a, let's say, a diaphragm moving back and forth, and you see compressions and rarefactions created in air. It's called a longitudinal wave because each particle is oscillating parallel to the direction of motion of the wave. And so this is a sound wave. Okay? And you can see each particle, air particle, is moving, oscillating parallel to the direction of wave motion. Okay. Okay, so it turns out that a sound wave can be thought of as a pressure wave. What this graph is showing you is, you see the pressure at this location. So what this graph is showing you is the pressure at this location is higher, the pressure at this location is lower. So here the sound wave shown as a pressure wave. This flat line would be atmospheric pressure. So at this location, the pressure is slightly higher than atmospheric pressure. And at this location, the pressure is slightly lower than atmospheric pressure. Okay, it turns out that your ears are sensitive enough where if the pressure changes by 1 part in a billion, you can hear that sound. Okay, so the softest sound corresponds to a pressure amplitude of 1 part in a billion atmosphere. And that's pretty amazing. All right, it can also be thought of as, what this graph is telling you is, it's telling you the location of the air molecules. So this is the air oscillating. So these, at this location, the air molecule is at rest. At this location, air molecules are moving, have a positive displacement. Some of these air molecules are moving in this direction, and that's why you have a high pressure there. At this location, some of those air molecules have moved in this direction, and that's why you have that high pressure. So some of these molecules are at there, some of these molecules are there, and these molecules were at rest. That's what this graph is telling you. Okay, so and we'll comment on that again. Okay, so sound waves can be considered either as displacement or pressure waves, and that's what we just said. So this shows you the displacement. So these air molecules were at equilibrium position. These air molecules, they have a negative displacement. Some of them are over here. And these air molecules, some of them have positive displacement. So some of them are over there. That's how you have a high pressure here, which is shown there. So this is a pressure wave. And this is a low pressure. Okay. So the sound wave can be thought of as a displacement wave or a pressure wave. And the pressure and the displacement wave are and there's a 90-degree phase difference between them. Okay, so that's the pressure wave is 90 degrees out of phase with the displacement wave. Okay, so we won't say much more about this. Okay, I just want you to be aware of it. So the sound wave can be represented as a pressure wave. Here's the amplitude of the pressure, sine kx minus omega t, and this was a wave traveling to the right. K is the wave number, omega is the angular frequency, as we saw last time. And the pressure amplitude is related to the displacement amplitude, like so. Rho is the density of the air or fluid in which the sound wave is traveling. V is the velocity of the wave. Omega is the angular frequency. Okay, so the two amplitudes are related. So sound waves in fluids are longitudinal waves. In solids, they can be both transverse and longitudinal, as we said. Sound waves will travel through any material medium, and their speed depends on the properties of the medium. Okay, so stiffer the medium, faster the speed at which they travel. Okay. So we'll talk about wavefronts. So here's, let's say, a point speaker. Wavefronts are crests that were produced at the same time. So this is the wavefront. That's a wavefront. And the reason wavefronts are important is at a given location, the wave travels perpendicular to the wavefront. Okay. So that's why wavefronts are important. And you can have planar, circular, and spherical wavefronts, among other shapes possible. So when you go to the beach, you see a planar wavefront, okay, or a straight line wavefront, and the wave is traveling, perpendicular to the wavefront. Okay. So let's see, maybe let's look at the ripple tank. Okay, so here's a ripple tank. So you can imagine a mass attached to a spring that's oscillating and hitting the water, and you can see circular wavefront. So at any location, energy is traveling perpendicular to the wavefront. Okay. So now we'll classify some of the sound waves. Okay, so the sensor that you are born with, sound waves can have any frequencies from 0 to infinity in principle. But the sensor that you're born with, your ears, you can sense frequencies from 20 hertz to 20,000 hertz. Okay. But of course, as people get older, they lose sensitivity to higher frequencies. So for instance, teenagers can hear up to 10,000 hertz, but older people cannot hear these high frequencies. And so you might have experienced some of this stuff in a high school classroom, where kids will have ringtones which have high pitches, and they can hear these ringtones while the teacher cannot hear the ringtone. Okay. So that kind of stuff happens. And on the flip side, some stores in malls that carry expensive stuff, and they don't want young kids to be loitering around, they'll play a high-pitched sound which annoys kids and will keep them away, while seniors cannot hear those sounds and they're fine in the stores. So anyway, that fact is utilized in technology sometimes. All right, human voice normally range from 80 hertz to 14 kilohertz. But interestingly, we can hear a higher range because in nature, you have to, for survival reason, you have to be able to hear a higher range. But here's the human voice range. Back in the days of low bandwidth, when bandwidth was expensive, telephones would limit to these ranges. But now with higher bandwidths available, you have wideband audio. And so nowadays telephones can emit a high range. But anyway, that's the human voice range. Okay, so infrasonic waves are sound waves of frequency lower than 20 hertz, so lower than what we can hear. And ultrasonics are ultrasonic sound waves of frequency higher than 20 kilohertz. So ultrasonic waves are frequencies higher than 20,000 hertz. Bats and dolphins use ultrasonic waves for echolocation. Large animals like elephants use infrasonic waves because infrasonic waves travel further and they're able to communicate over larger distances. Whales use infrasonic waves as well. All right, so the speed of a sound wave, speed of any mechanical wave depends on the elastic property of the medium divided by the inertial property of the medium. Okay. So for instance, so you will see in a second that the velocity of longitudinal waves depends on bulk modulus divided by the density of the fluid, and velocity of transverse wave depends on the shear modulus divided by the density of the medium. It turns out that the bulk modulus, so this is for longitudinal waves, and this is for transverse waves. It turns out that the bulk modulus generally is greater than the shear modulus, so velocity of longitudinal waves is greater than one velocity of transverse waves. Okay. All right, so the velocity of a wave depends on the elastic property divided by inertial property. Okay, so for sound, so in fluids, for longitudinal waves, it's the bulk modulus divided by the density of the medium. Okay, so for longitudinal sound waves, it's bulk modulus divided by the density. And here is a table list of velocities. So in air, the speed of sound is 340 meters per second. And notice in solids, it's about 15 times greater. Okay. So, or yeah, 3 times 2, 15. Yeah, so 15 times greater. Okay. In water, it's about 5 times greater. So the speed of sound is about 5 times greater. Okay. All right. So that gives you the speed of sound in various medium. Okay, and now the speed of sound depends on the temperature as well. Okay, so in air, so this is the speed of sound in air, and here's the bulk modulus in terms of the ratio of specific heats and so on, which you'll learn about in physics too. But here is just the temperature dependence for speed of sound in air. This is the temperature in this Celsius scale. 273 is if this temperature was in Kelvin. So this is this formula where the temperature is in Kelvin. Okay, so it turns out that so this is the speed of sound at 0 degrees Celsius. And so for every degree rise in temperature, the speed of sound increases by 0.6 meters per second. And below 0 degrees, for every negative degree below zero, it decreases by 0.6 meters per second. So this is this dependence on this on temperature. Uh, Generally, room temperature is about 20 degrees Celsius, so that would add 12 meters per second, and so at room temperature it's about 343 meters per second. Okay, so here's just a little fun fact. You guys have all watched fireworks or lightning, heard lightning and so on. Okay. Light travels almost instantaneously compared to sound. So here's the speed of light compared to the speed of sound. Light has a speed of 300,000 kilometers per second, and sound travels at 0.3 kilometers per second. So light travels 1,000,000 times faster, almost 1,000,000 times faster. So here's the 5-second rule. If you hear the thunder 5 seconds after you see the lightning flash, then that means the lightning is a mile away. So if you hear the thunder 10 seconds after you see the lightning flash, that means the lightning occurred 2 miles away. Yeah. All right, so I will let you guys read this stuff later. Seismic waves are mechanical waves that travel through Earth, or they're sound waves that travel through Earth. And since most of the Earth is a solid, both longitudinal and transverse waves can travel through the medium. And as I said, the bulk modulus for solids, for most materials, is greater than the shear modulus. So longitudinal waves have greater velocity than transverse waves. And okay, so the bulk modulus of granite is greater than its shear modulus. For this reason, the speed of longitudinal or pressure waves, they're also known as primary waves in earthquakes, is significantly higher than the speed of transverse waves or shear waves. Okay. Both types of earthquake wave travel slower in less rigid media, such as sediments. So anyway, the primary or pressure waves have a speed range of 4 to 7 kilometers, and S waves have a range in speed of 2 to 5 kilometers. Now, you learn that as the speed changes for a wave in a medium, it'll bend. Okay, and so I'll show you a slide in a second. Okay. So the time between P and S waves is routinely used to determine the distance to the source, to their source, the epicenter of the earthquake. So here's a picture. The internal structure of the earth was learned using these waves, how they travel, how they bend and stuff like that. So here's an earthquake occurred here, and all those earthquakes were determined by seismometers around the earth. Okay, so from the data collected in seismometers all around the earth, you can you can reconstruct the path and then calculate the properties of the materials. Okay, so for instance, we know that, see, the outer core is liquid, and S waves, transverse waves, cannot travel through liquid, so only P waves travel through liquid. And that's how come we know that this outer core is liquid. Okay. So you see the earthquake occurred here, and S wave traveled only till that point. Okay. And this is all shadows. For there's no S wave reaching these points on the earth. Anyway, so from studying how these waves travel, we know we have reconstructed the internal structure of the earth. Okay, now we saw that all waves carry energy. Okay, so sound waves carry energy as well. And we are interested in how much energy is carried by the waves. Okay, so here's how the sound wave is produced. This piston is oscillating back and forth, and that's what's pumping energy into the medium, and that energy travels with the wave. Okay. So the power, so you can stand at any location, and the energy that crosses you per second is the power, and that's equal to 1/2 rho is the density of the medium through which the sound wave is traveling. A is the area of cross section, so area of cross section of the piston. V is the velocity of the wave. Omega is the frequency of the piston and of the sound wave, and S is the maximum displacement of the air molecules. So that's the displacement amplitude. So that is the power. That's how much energy is passing a point per second. Intensity of the sound wave is power per unit area. Okay, so how much energy is passing per unit area per second is intensity. Okay. And that's, again, rho is the density of the fluid, V is the velocity of the wave, omega is the frequency of the wave, and S is the maximum displacement amplitude. And here is the intensity expressed in terms of the pressure amplitude. Okay. So this is the pressure amplitude squared divided by 2 times the density of the fluid times the velocity. Okay, so here is a point source. A point source is something that emits sound waves in all directions. And then, so this could be a bird singing. And what this formula shows you is the intensity is the power of the energy that the bird is putting out per second, or this could be a point speaker, an omnidirectional speaker. That's the power of the speaker divided by 4 pi r squared is the surface area of a sphere. So the intensity at distance r is given by P by 4 pi r squared. Okay. So a point source will emit sound waves equally in all directions. Okay, so we are born with several transducers. Transducers are devices that convert one form of energy into another form of energy. Okay, so our ears convert mechanical energy into electrical energy. So the sound waves that impinge upon our ears are pressure waves. The ear is a transducer that converts sound waves into electrical impulses, nerve impulses. Your tongue, for instance, converts when certain food molecules bind to this taste buds. So that is converted to chemical energy, is converted to nerve impulses. Your eyes convert electromagnetic energy through photons received into electrical impulses. Okay, so you are born with various transducers. I suggest you guys check out this YouTube video. It's quite good. Okay, so anyway, when sound waves travel, they set your eardrum into vibration, and that is transmitted via these 3 little bones into the cochlea, which is where those mechanical vibrations are converted to nerve impulses, into electrical energy. All right, I will pause now for a second and let you guys ask questions if you guys have any. Okay.